The purpose of this lecture is to provide a supplementary recorded lecture to give you some additional information and background regarding the voltage synthesis for AC motor drives, which is really kind of a core thing, a common thing that will apply to every type of AC motor drive. And there's a few things that I want to make clear that will enable you to make some analytical calculations around a drive. So there's a lot that you can analyze without having to do simulations. And that's really the point of this supplementary lecture. But there's a few things that you've got to understand that I don't think may not be 100% clear to everyone, especially if you don't have a strong understanding of power electronics. So to start with, I'm going to talk about this generalized structure for an AC motor drive controller. Now this applies to any AC motor drive in general. And in fact, any motor drive so far, what I'm showing you applies. So this block right here, and maybe to just make that distinction, I'll put a little highlight around it, because very soon we want to try to synthesize what we know about all types of motors into how do we control them with closed loop feedback control. And so this is pretty common, these 4 blocks for any drive. What they consist of is that, first of all, you've got set points, and the set points may be generated from a human interface command that they want the motor to follow, or they might be generated by a plant process of some kind that is calculating the set points needed for the motor to achieve its objectives. The next block I'm just calling in general, and really these 2 blocks together, I will call them command synthesis / generation. So you take the set points and then you need to convert them into commands that can be followed by the motor drive system. And so as a minimum, if they say the set point is a speed set point, so I'll just kind of draw this down below. Let's say that you've got a mechanical speed set point that you're wanting to achieve, and I'm not going to put a star. I'm going to call this omega m set point. Okay, so the set point here maybe if this is a closed loop system, then there's really nothing that has to be done right here. So this particular block here is just a pass-through. But then here you need to ramp the set point. So you basically know that you're going to start the motor, say, at 0 speed, and it needs to go up to the set point value, because you can't just step from one point to another. And actually what happens here, I guess, is really to calculate the ramp rate. So that's at least one thing that has to happen in this block before then. How fast can you ramp the speed from one point to another has a lot to do with both the plant that you're controlling and the motor itself. So as a minimum, this block right here would be finding the ramp rate and putting some meaning on that. And then when you're coming out of here, what you have is the actual speed command. So the command following portion, command following portion for this closed loop control means that you would actually have to have feedbacks to make sure that the command is followed. Or you would need to have a plant observer of some kind. So let me show two ways. Here's your feedback. This is your, say, closed loop approach. So it would take the omega m star, and it would compare that with the feedback that's coming from a feedback sensor. And then you would need some kind of a controller here to force these two to follow, to force command following. And so the most common is the proportional plus integral. And then what comes out of here, if let's say that we're going to go right from this point to the motor, drive control, there's no other internal closed loops, then this is the complete command following block. So I'll put that right here, and essentially what I'm showing is that. And then I'm going to show up here that you might have feedbacks coming into command following. You might have other information coming in there as well that's helpful. So when I don't kind of represent that, so I'm going to put that here. You may, if there's a closed loop, you would have that. So I'm going to make this gray because it's not always there. Okay, now this is where it starts to make a distinction between, say, a DC motor drive and an AC motor drive. So what comes out of command following is the voltage commands that are going to your modulation or your, let's say, switch state synthesis to make things completely generic or general. And so at this point right here, we can say with certainty of generality that for the AC, three-phase AC machines, and I'm excluding brushless DC, and I'm excluding the standard DC motor here. Really, we're talking about fundamental component controlled motors. We have the VQD command, so I'm showing that as one symbol representing two voltages. And to clarify what we mean there is anything where I have, in general, any variable, I'll call it FQD, is FQFD. If we're showing it in matrix form. And then we're going to show later on that we can show this same thing in a vector form where we could say VQ minus JFD. So it could be any one of these two representations depending on how we're mathematically looking at this motor drive system. And now at this point, we have to do a transformation. And that was what I really am trying to make clear. And so at this point, we've got the rotational transformation. So at this point, what we need to do is we need to go from the QD reference frame into an ABC reference frame so that we can do our pulse width modulation. So this transformation matrix is actually an inverse transformation. because we're going from QD to ABC. And then from that, the output of this is going to be the ABC commands. And these are the commands that we're giving to our inverter. That's why I'm putting a subscript I. And I could put a subscript I right here as well. So this is what the voltages that we want to synthesize from our inverter. And so what we're doing here is we're taking something that would be in the synchronous reference frame. If we're using the PI regulation, then we want to have quantities that are going to be DC in the steady state. We're converting these effectively steady state DC values to three-phase AC. The angle then would be the synchronous reference frame angle, because that's what we want to apply to the stator of the machine. So we know that this inverse transformation matrix is, and this is a generalized expression, because I haven't, as you noticed, made any determination as to what VQI commanded is. So this would be synchronous frame, and it's a command, but I haven't said what they are. So as a result, the general result here, if I multiply everything through, will be this expression here. And so if, say, VQI star is equal to Vs, and VDEI star is 0, then VAI star is Vs cosine of theta, VBI star is Vs cosine theta minus 2 pi thirds, and VCI star is Vs cosine theta plus 2 pi thirds. On the other hand, if, say, VQI star is 0 and VDI star is Vs, then VAI star is Vs sine of theta s, VBI star is Vs sine theta s plus 2 pi, or minus 2 pi thirds. VCI star is Vs times cosine theta s plus 2 pi thirds. Now, the next step in the process that we've described up here is, since we have references that we've created, we're going to apply pulse width modulation techniques here. Then that would go right here. Now, the pulse width modulation approaches that we could apply fall into, so far what we've discussed in class, two types. We've got what we were calling the sine triangle PWM, and we're going to call this S-PWM. We've also talked about space vector. One more thing that we have to have for this whole thing to work, as part of our command following algorithms, and you'll see this emerge as you look at the different approaches to synchronous motor, induction motor control, is that you have to synthesize the stator angle. So this angle synthesis requires, as a minimum, some either angular feedback if we're doing anything that involves a form of vector control, and that would be, say, coming from an encoder or resolver. And remember, with the synchronous motor, the angle that we would be sensing, say the mechanical angle, times the number of pole pairs plus a torque angle, that becomes theta r plus del, which is theta s. So we have already been through this with the synchronous motor. It was really pretty straightforward. But now when we look at, let's say we looked at the induction motor, we've looked at volts per hertz so far, and with the constant volts per hertz we had there was no angular feedback. And so instead, as part of the command following, we would be synthesizing the angular feedback for volts per hertz. So constant volts per hertz control of the induction motor would basically take the commanded synchronous frequency and integrate that frequency to get theta s. Or this would be a 1 over p with the notation that we're using. And I also had shown in some of our notes that you might have a remainder function here so that this theta s rolls over when it hits 2 pi. That's really in the actual implementation of this thing. You'll see ultimately what comes off of the encoder has to be processed to make it look like this. The resolver will give you a much direct measurement that looks just like this with the resolver. Now we will learn with the field-oriented control of the induction motor that this block right here is more involved, much more involved, and really plays a key role in achieving torque control of the induction motor. So let's step back and look at this whole thing. We've got this generic structure starting from the set points. We've got the command synthesis generation, the command following implementation of closed loop controls, essentially. In order to make those controls, or if it may be open loop, and that's why I made this gray right here, because it may not be there. In order for the command following to work, it has to generate references that the pulse width modulation can follow in order to force the gates to do the correct job. And to be consistent with the color schemes I've been using here, let's make this angular feedback part here gray, because it may not be necessary with all approaches to AC motor control. We've already seen, for example, the constant volts per hertz control would just use this part right here. I don't want to go too crazy with my color codes, but if you had a synchronous motor, as we showed, you wouldn't have to have this part here. You would just have this part. Maybe this might be an angle or something. So I guess technically there might be something there, just an offset. So anyway, that's your general overview of what goes into the voltage synthesis. But this is really where voltage synthesis occurs, right here. In combination with whatever the transistors do in your inverter, that's how you synthesize the voltage. So I want to drill down onto this just a little bit. That's the whole purpose of this supplementary lecture. So let us consider the drive right now. Recall, this is a simple DC fed AC motor drive. The motor that I'm showing right here, that could be a induction motor or a synchronous motor. We've got the 3 half bridges. So you've got a half bridge for the A phase, a half bridge for the B phase, and a half bridge for the C phase. Then we've talked about how we would have switch states for each half bridge, SA, SB, and SC. So we said if I can zoom in this here just for a moment to clarify, we call this the transistor Q A upper and Q A lower, QB upper, QB lower. And we treat this, even though you've got a transistor, an IGBT, and a diode in parallel, it's like one switch that can pass current in 2 directions. We have the QC upper and the QC lower. So I wrote that out to explain what we're doing with these logic states. If SA equals 1, QA upper is on, and QA lower is off. If SA equals 0, QA upper is off, QA lower is on. And the same will go for these other 2 phases. So we've explained that before. I'm really, in all of this, just talking about gate control logic for the synthesis of voltage. There are other things involved in the gate logic. There's gate logic for what we call dead time. I'm ignoring that right now. So if I were going to include that, I would have to have individual states for all 6 devices. And I'm not really talking about gate. That's a power electronics problem, really. We're just really talking about the theoretical synthesis of these voltages. Now, a couple of other points here. We're going to designate nodes in this circuit. We have the A node, the B node, and the C node here. The A node has a line that goes to the stator A phase connection, and then the B goes to the B and the C goes to the C. We're going to assume a neutral connection here. If it was a delta connected winding, there would still be a virtual neutral. So it's completely correct to express things this way. Now the reference, so you can think of the voltage from here to here, this is what we're calling VAS. And this converter needs to synthesize the voltage from the A point ultimately to the neutral point. But we're at this other end, and we said that when we talk about the synthesis of the voltage at the terminals here, we think about each line with some arbitrary point on this circuit as a reference, and the most convenient point to pick is the midpoint, and that's why I made these capacitors gray. This may not physically exist, but the circuit is symmetrically laid out, so it's going to behave as if this node does exist. I'm sorry, I'm getting a little crazy with the gray. So it will behave as if that does exist, even though it's a virtual point. In the same way that everything is going to behave as if that point exists. It's really a kind of a symmetry that occurs in any electrical circuit. We don't really think about it in DC circuits. It does exist because there are things called common mode, and that we have to understand this to understand common mode. In this circuit, we must understand this point in order to completely understand the shape of the voltage that we're applying. So we are missing one other voltage point that we haven't talked about yet. That is that there will be, effectively, if you could physically make this, you could measure this. And there would be a voltage V from this 0 point to this end point right here. And I've actually measured this on power electronic systems, and the averaged of this voltage, so the average of V from 0 to N is going to be 0. But there's going to be AC component on this voltage. So the AC content of the V sub ON is related to the common mode voltage, or we could call it the zero voltage. And that zero voltage is when we first introduced the DQ transformations, we had, going from ABC, we would go to DQ, and there was a third zero. We dropped that zero so far. This was actually a 3x3 matrix being multiplied times whatever was the ABC over here. And so this term here relates to this. And it really was, if you recall, the transformational matrix. I'm not going to write everything that was in it, but there was a 2/3 multiplier on the outside, and so filling in the bottom row, we had a 1/2, a 1/2, and a 1/2, and so the V 0 here ends up being VA plus V. So I'll just say this is a VA 0 plus V B0 plus VC0 divided by 3 is what it'll end up being there. And that is the definition of common mode voltage. We also talked about how these switch states of S, A, B, C can be represented in this hexagonal form here. And we talked about how you can think of how this was created. Was we had along the x-axis here, we had an A phase, and then this point right here is 120 degrees away, and so that became a B phase. And then we had another 120 degrees. And a resulting C phase right here. So these are basically axes for the stationary reference frame ABC voltages. And if we thought about synthesis of voltage, we talked about how we could have a moving phasor at this angle theta S. And as that phasor moves around, it would reflect onto these three axes, A, B, and C. This phasor moving around is really what we're trying to synthesize, is the VS. So we could synthesize it in ABC. We also said we could synthesize this in alpha beta. So I'm going to draw another little line right here. If you added a 90 degrees right here, then you would have had your beta axis, and this would have been your alpha axis. That was the same as the alpha was the stationary frame Q, and then the beta, actually the beta's down here. That was the same as the DS axis. So you're talking about reflecting this onto different axes. And that's how you synthesize, think of voltage as being synthesized. And then we used the pulse width modulation, meaning the amount of time that would be at each one of these states to synthesize this voltage. And in order to get a voltage, we would have to have two more states. These would be zero states where we're not applying any voltage. We're applying a zero voltage. So we would have either a 0, 0, 0 or a 1, 1, 1 state as well. Now, what I want to talk about is, what if we did not use these zero states at all? So there are no zero states. We could actually, we've talked about two types of PWM methods. We talked about the SPWM, and then I think just double checking here, yes, we talked about the space vector PWM, which we called SVM here. So we talked about those two PWM methods, and with either method, if you just let them naturally run against the references, if you have the sinusoidal PWM method, you are only able to synthesize controllable voltages a circle fitting within the hex that I've shown here, the hexagonal shape. So I'll try to represent what I mean by that. So what I'm showing here is that I've got this circle inscribed inside of the hex. Here's your phase voltage Vs that you're trying to synthesize, and the amplitude of this arrow is reaching out to it's reaching out to the end here. If it's of this circle, that's the maximum amplitude that you can control within this hex using standard sine triangle PWM. What this represents, the magnitude of this phasor, that magnitude right there is the peak voltage magnitude. And so what that is, what the peak voltage magnitude that is representing, which is the the length of the vector, that is equal to the peak phase voltage that's being synthesized by the inverter. So the peak phase voltage would be square root of 2 over 3 times whatever, say, the line-to-line voltage is that you're trying to synthesize. And that's really what we're calling Vs. So I want to make that super clear. If we increase the size of this arrow, then we're just increasing the V line to line. But once you go out beyond the circle, what happens? You can't produce any voltage higher than this line right here, than the hex. So that limits the voltage that you can produce. And it's related to the DC link voltage. Now in sine triangle PWM, if you go beyond this point right here and you're operating out here, what you're actually able to, you can produce a higher voltage but with low order harmonics. Otherwise, when you're inside of this circle, so we're inside of this, we synthesize this peak voltage by dwelling a certain period of time at this state here. And this is, we're in what's called sector 1. We go a little bit of time on this state, then this state, the 0 state, and then we go back the other direction and go back to this state and back to this state, and then we go back to a 0 state. So we're always going around this triangle to synthesize. Once we get beyond the circle, essentially this 0 doesn't do much good for us. 0 state in the sine triangle, it doesn't allow us to synthesize the sine wave exactly. We will have lower harmonics. So what I mean by that are odd harmonics, third, fifth, seventh, etc. Once we get to the point to where we are operating all the time on this boundary here, as we go through all of the 6 sectors, we're not using the 0 state at all. So what does this mean as far as what does the voltage look like? So if I'm out on that boundary, this is what is happening. The voltage from A to 0 is going to stay constant over 2 sectors. So say I'm starting in sector 1. This point right here, I'm at a state. So this is this voltage amplitude right here is the DC voltage divided by 2. And then this amplitude here is negative VDC divided by 2. And the idea of the pulse width modulation is for me to alternate between these 2 states. But when I'm writing on the outside of the hex, and I can only operate in one state or the other, and I'm looking at a period right now. This is a full period right here that would be 1 over Fs. So that's 1 over the synchronous frequency that I'm trying to achieve. And you can see what's really happening. If I'm in sector 1, so right here, sector 1, it's between these 2 points right here. When I'm in sector 1, my VA0 is connected to the top rail, so it's going to go halfway between. It's going to be VDC over 2. That means that it's the SA is equal to 1. See, was I using capitals? Yeah, I was using capital letters there. Go down to the SB. The SB is connecting to the negative rail, so the SB is a 0. The bottom switch is on. And the SC is a 0. So I'm at the 1, 0, 0 state. Then when I get to sector 2, I've got SA equal 1, but now SB equals 1, and SC is equal to 0, and so on. So you can see that as I'm traveling in this direction here, that's representing me going along this outside. So I'm in sector 1, and then I got to this point. I'm in sector 2, and I'm traveling on the outside. I'm going in this direction. And we call this directionality, we call it, because we're going in this direction of these arrows, we actually call this positive sequence. And that actually relates to the direction the motor's going. If we wanted to go in the opposite direction, it would be effectively a negative sequence. What we're doing when we go the opposite direction, and I'll show you that up here. If you go in the opposite direction, you're going to take these signs and flip them. So the B and the C, you make a positive here and a negative here, then that would mean you're going the other direction. And that's why when you change the the A and the swap any two leads on a three-phase motor, induction motor, for example, which is a really great example because the induction motor is just going to run in the one direction or the other, and if you swap the two leads, it'll go the other direction. And then this is showing you what's happening. Well, what we're doing by creating these voltages, the VA to 0, the VB to 0, and the VC to 0, is that we're actually creating a common mode voltage. It's a low frequency common mode voltage because there's no high frequency switching going on. They can't, because we can't. What gives us the high frequency switching are the zero states that allow us to synthesize a voltage. And so the common mode voltage is equal to the sum VA0 plus VB0 plus VC0 divided by 3. So we can actually plot that, and I said before that VA0N is the same as the common mode voltage. So I've just summed the three voltages and plotted them here. And what you notice is you go along that you've got the voltages going positive and negative, and the period here is 1 over 3 FE. So it's really effectively a third harmonic. Now if you want to get to the voltage applied to the phase of the motor, so remember that we have VAS, that's what we're trying to apply. That's equal to the voltage from VA to a neutral. So let's go look at the circuit for a moment and understand that. So the VAS is really this point right here. That's the A point to this neutral point. The B, same thing, from this point, from here to the neutral. That's the full voltage across the phase, and the C as well. So then from the neutral back to the zero, because this is what we're synthesizing by switching back and forth between plus and minus VDC over 2, we have this. And so the VAS is the voltage from A to neutral, which is the same as saying the voltage from A to 0 plus the voltage from 0 to N. So we were just adding them up. So if we look at that here, that's what we're doing. VAN is VA to 0 plus V 0 to N. That's how we're synthesizing this voltage right here. So that's the VAN, this voltage, just adding them up. So we have a very interesting thing. If my phasor vector, that is the phasor that's moving around, is moving around on this edge here, it's physically going to reflect onto the three phases looking like this shape. And this actually is a shape that has a, we think about a Fourier series representation of the different frequencies involved. You've got a fundamental frequency, obviously. So that would be your FS1 or the FS. But you've also got a third harmonic involved here. Those are the most dominant harmonics. You've got other odd harmonics. You've got the fifth and the seventh. It's odd because there's no even harmonics, and that's because the voltage is symmetrical between the positive side and the negative side. If it was not symmetrical, you would see even as well. But so this is at Fs3, third harmonic, or 3 times Fs. So you actually have a dominant third harmonic. Now, what does space vector modulation do for you? Space vector modulation allows you to synthesize a controllable voltage inside of the hex. It doesn't have to be a circle inside the hex. So that means that we can use the full area here and synthesize our voltage and we do it without any low order harmonic distortion. Now the question is, how do you actually accomplish that? Why is it that possible to do that? The bottom line is that if you've got a third harmonic voltage, what it looks like is this. You've got the VA and third harmonic is going to be some amplitude associated with that harmonic. If this is a cosine, it's going to be 3 times theta s. If it's a VBN, it's going to be V3 cosine 3 times theta s minus 2 pi thirds. And the VCN 3 is V3 cosine 3 theta s plus 2 pi thirds. So the interesting thing is this, that if you multiply through the 3 in these then the second term here, the offset term, these two offset terms become just 2 pi. So what you've done is you're just adding them up, and they just become a constant. They don't add up to anything at the frequency of theta s. So if you sum these triplet harmonics that are produced by once you introduce a third and you sum them up with all the other harmonics, essentially the currents in the motor don't see the third harmonic. So I could go through, it'd probably take me another 45 minutes to explain this in detail, which I don't want to do. So just accept that fact. So you can actually put a third harmonic onto your sine wave, and you can synthesize what you want without you having to introduce any low order harmonics. So I'm going to show that in a simulation in a moment, but now let's talk about what this means. the phase voltage right here defines the condition, the maximum line to neutral voltage that we can achieve for any given VDC. And it also tells us the minimum VDC at which a given phase voltage can be achieved for a particular VDC voltage. So, and let me repeat that again. It's giving you the maximum line to neutral voltage that you can synthesize given VDC, or it tells you the minimum VDC required to achieve a phase voltage. So if you do the Fourier analysis on this waveform here, you will get this term for phase AN. It's going to be cosine. This is going to be the fundamental component, and that's the thing that you're interested in. This is what you can use to drive your motor. And so this is essentially the VS max that you can absolutely achieve for a given VDC. So that's what this says right here. So if I asked you what's the maximum voltage peak that you can achieve, it's going to be 2 over pi times VDC. If you wanted to know what in the book it calls V phase max, would be the RMS value of this. So it's taking this peak voltage and divided by square root of 2, and that's how we come up with 0.45 VDC. So the maximum voltage, let's say for a 300 volt DC link, would be 135 volts. We can't achieve any more voltage than that. Now, I invite you to look at my notes for these lectures, which are posted, and go through the example with this understanding. And I'm just going to give you a little more insight by looking at the simulation that we have. Okay, so what I've got here is I've got a simulation running of this induction motor being controlled by volts per hertz, constant volts per hertz controller. And this is what the model that is up on D2L. It's called volts per hertz controlled induction motor. That's up on Canvas. What are we doing here? Well, what I've done is, just to take you quickly through, we've got a speed command coming in. That speed command is converted to the synchronous frequency. Then that can be ramped at a ramp rate. And then these are the equations that are also in the textbook for the constant volts per hertz ratio and the voltage offset. And then this is the peak voltage that's synthesized. And we're simulating with a DC bus voltage that is at, it's around 600 volts. So you can see the DC voltage here. And actually I want to point something out. This has got an AC fed with a diode bridge. So we actually have a realistic simulation going on, and I'm looking at the grid side currents through the diode bridge. This has nothing to do with the pulse voltage synthesis. I just want to point this out. I'm showing all three of those currents. If you just can look at, here's one period. They're extremely distorted. These are the pulses that are going through the diode bridge. And these are the currents that are being synthesized into the motor. So we're actually putting really nice sine waves into the motor. And this is the mechanical power that's being applied to the shaft of the motor. So it's a model that works very well. And we take the voltage reference right here, Vs, that becomes the VQE. The VDE is 0. This block takes a 0 reference, so I have to give it a 0 common mode reference. It takes a 0 input, and I'm going to put out ABC here. So these are your 3 voltage references, and these would be the sine waves of the voltages that I'm wanting to produce before I divide them by the DC link voltage, which is the rated DC link voltage divided by 2, scales them down into effectively duty cycles. Now, and this is the frequency synthesized here, with the frequency being integrated right here. This is that remainder function, and that's the theta or omega t that gets applied here. Now, what I've done, this is if I'm mimicking what a space vector PWM can do, and that is by introducing a deadband. And this deadband, this is the math behind it. But what it does is it actually injects a third harmonic on top of the references. And so it's called third harmonic injection into the sine triangle, PWM. This is something that Graham Holmes pointed out, that he and Tom Lippo had written this famous book about pulse width modulation. But in an early paper in the 90s, he pointed out how you could simplistically create the same thing that's quite complex in space vector modulation, as long as you have analog controls, that would be exactly as good as space vector control. And so now these are the per unitized references that I'm working against with my pulse width modulation. And I want to show you what they look like. So this is the voltage references in the triangle compare and the switch state synthesis. It's a little easier. I'm zooming in too much. Let me zoom out again. There. So we'll look at the shape. So instead of a sine wave reference, because I introduced the third harmonic, I put this little flat top on it. And it doesn't, you saw how nice the currents were. They're very sinusoidal. Now what the motor can't see the third harmonic that I'm putting in. Let me increase this frequency command and overspeed this motor, and I'll show you something. So right now I was commanding this R1800. Why don't we try 1900? Higher speed. It's going to ask for more voltage at a higher speed because of the constant volts per hertz. And we're going to run it again. And I've got to wait until it ramps up. Okay, so I ran this again, but I'm still within the plus and minus maximum. If I'm under the 1, that means that I'm below VDC over 2 or minus VDC over 2 envelope. So I'm going to increase the frequency a little higher. Okay, so you can see here that I am still underneath. I'm getting closer to the top of the peak, but I'm going to show one other thing. I'm going to plot the reference before the deadband now on top of this. So now what we can see here, if you look at this red line, and that's that's the reference, the duty cycle reference for the A phase. And the blue line has the deadband for the third harmonic on top of it. And so the red line is going above this point. Essentially, this is the peak VS that is being synthesized, but you need to have this extra space in order to reach the top of the hex. And the third harmonic injection allows you to do that. Once you get to the point where, say, this blue line would go up, these lines right here go above there, then you're outside, you're trying to command what's outside of the hex, and you're not going to be able to achieve that. You'll be able to get a higher voltage, but with a lot of harmonics. And if you keep going higher, you'll get to the point to where you can't synthesize any pulses at all, and the waveform looks like the square wave. I'm going to try to do that, and we're going to go look at the waveform again while this is running. I'll go all the way to 2500, and let's see if we can force it in well into saturation. I'm indirectly increasing the voltage by commanding a higher frequency here. And let's look at what we mean by this. So we're looking at these waveforms again, and if you think about what the A to 0 voltage that can be produced is plus minus VDC over 2, and what that represents. So if we said that we had sine PWM, then the VS, which is the peak voltage, would be equal to its modulation index times VDC over 2. And when we get to this VDC, if we're asking for a VS that's, say, if VS greater than VDC over 2, or let's say it's equal to that, then MI is 1. That's the peak. So that would be saying I'm trying to get a voltage that's hitting right to the peak right here. So that voltage, let's change the color so we can be clear about this. Okay, so that's this green voltage right there. That voltage is inscribed inside the line. If I try to go higher than that voltage, so I'm showing here, if I can push the circle out to the corners, which is what I've tried to do with this lighter green circle here, that's basically saying that I'm able to do that with space vector PWM or this third harmonic injected PWM, which is called zero sequence PWM or ZS PWM. And by what I've done there is I'm running right on this, and the results are that the synthesized voltages against the references, when I am running below, I'm actually show this just above, so it'll show I'm actually going to get switching between every parts of the waveform that is inside of that VDC over 2 envelope. So for the green one, obviously it would be pulse width modulated all of the way. And the same thing with the other 3 voltages. If I went up you can see here that I'm starting to skip pulses because this little line is going above. But if I were to come just below, or I was operating like that, I'd actually, what that's doing is it's giving me more voltage than I could get out without the ZS PWM, because the fundamental component of that voltage that I would be producing would be actually higher. So the amount of voltage, additional voltage I can get above this level is 15% higher. So what that means is that if I'm applying ZS PWM, then the I can actually get to a VS equal to 1.15 times VDC over 2. So this is the maximum controllable PWM voltage. This would be the MI max that's controllable. So there are actually 3 different modulation indexes that you might be concerned about that we've talked about so far. We've got this first one here. So let me just list them. Number 1, the first one we talked about was when we aren't PWMing at all. We have no pulse width modulation. And that means that we're outside of the range of voltages that we can synthesize. So we're just going to run at this 6 pulse. It's called 6 pulse behavior because there's 1, 2, 3, 4, 5, 6 pulses over a period that are being produced. And so we have a max, let's say max 6 pulse modulation index. That is actually going to be 2 over pi times VDC over 2, being equal to VS. And so this would be that modulation index. So what is that? MI max in 6 pulse. It's 1 over pi. The second one is we could have MI max, and we're actually using 0 sequence PWM. And that ends up being 1.15 times VDC over 1.15 is the value. Go back to this. Basically, I'm saying I've got the VS max, that absolute max I can achieve for a given VDC is this, but I'm just 6 pulsing with no control. Controlled, I can operate with this modulation index, and so the VS max controlled with ZS PWM is going to be 1.15 times VDC over 2. And then the third one is the MI max sine PWM is just 1. And so the VS max, without having any harmonics or any problem, the VS max controlled with just sine PWM is going to be VDC over 2. So you've got these three possibilities. So there are questions I'm going to ask about that will require you to either find VDC min or VS max with various considerations. And this is very important, and this will be on the final exam. So I want to make sure that you understand this very well. Now let's just take a look at the simulation for a moment. Okay, so finally you can see what I was talking about here. I'm actually running outside of the envelope. So we're almost a square wave. We still have these pulses right here. It's hard for me to force the exact 6-step behavior with the sine triangle PWM because of this. I'd have to apply a square wave reference. I'm applying a sine wave, and so when it goes above this point right here, it's flat. And so you can see what's going on there, and I'm approaching the max, absolute max modulation index here. What does this actually do to the current? So let's just, for fun, look at the motor. So you can see they're not too bad, but I'm starting to get some low order harmonic behavior. The motor makes a really good filter, but this will introduce torque ripple. You can see how it's getting kind of bent over, and that's because we're in the overmodulated mode of operation.